Hi, I'm Eleonora, by the way. I work at the Imperial College in London. Let me share screen one. Share. And I hope you all enjoy my background. And what do I do there? There I am a teaching fellow in materials, which means that I teach undergraduate students, and I'm also head of outreach within my department. So today I would really like to tell you why material science is awesome, and why I think about that all the time. I think it's a fantastic, beautiful discipline that I have started to love since I got to know that it even existed, because not many people know that it's even a discipline. So let's get cracking onto it. So who am I? I am a person like anyone, really. I was a kid. I love cream, as you can see from my pictures from before and after, with cream, with sugar. I love singing, and I don't love dancing. I'm really, really bad at it. And I used to be in a choir with a group of my fantastic friends who became my best friends nowadays. I love drawings as well. So I was not born a scientist. Do not think that I used to be a scientist when I was a kid. I am just a really normal human being. How did I get to do material science, and why there is toothpaste over there? Well, that's the question that my mom would ask me 24/7, pretty much. When I was a kid, I used to be one of those kids that would put together all of the different materials from the house. So you would have toothpaste plus oil plus flour plus hair wash, and I would just wonder what was that going to become and what was that going to be. The answer was always nothing particular, and the answer mostly was just my mom getting really angry at me for messing up the house. But I guess this is a really normal and common thing to do for kids which didn't have an iPhone at the time. So yeah, this is what I used to do. And then growing up, I slowly started learning a bit more about material science, not knowing that it was a discipline still. So I saw some fantastic materials. One of this was this beautiful material, which is called a ferrofluid, which is a suspension of iron particles within an oily suspension. And that means that it gets attracted by magnetic fields, and it creates these fabulous shapes which move around. It's glorious, and that was one of the first things that I bought with my own money, and I was just really happy to be playing with it. What did I do after that? I started to study it. I did an undergraduate degree in material science, and then I went for a master's at Imperial College, where I graduated, and then I did a PhD as well at Imperial College. I seem to never want to leave Imperial College, apparently, but it's a really fun place to study and work. And now I'm there. Now I'm just teaching there 24/7, pretty much. There's never a break. But let's get on to what material science is actually, and why we're all here to discuss about it. So first things first, material science is what? I imagine you've all have heard of materials. Materials are all around us. Material science means the science of stuff. It's literally everything that is around us, from your phone to your water bottle to your mouse mat. I'm literally just naming stuff that is around me. Everything is made of materials. And if you think about it, everything has been made and developed by material scientists in a way or another. Whether they were engineers or product developers, they were all doing material science. In particular, there will be loads of applications that you might have seen. What do? We work in aerospace, we work in automotive, in nuclear, in biomedical. We do materials for sports so that they become light, strong, resistant. We develop musical instruments to increase the acoustic, for example, of guitars, and we choose the precise materials that would work on that. We work in the biomedical field, where we create prostheses that can go into your body without being rejected by your body. And we work to make lighter and stronger aircrafts. These are only some of the things that we do. And today I would like to just give you a few examples of what we actually play with most of the times, or that's what I play with most of the times. So that you can get a bit of a better idea of what material scientists actually do. So a few examples. One of the first examples that I find always so much fun is a friend of mine actually was working at the synchrotron, which is a particle accelerator that is based in Didcot, not far from Oxford. And in this environment, he was paid loads of money to study chocolate. You would not believe that. I didn't believe that until I heard that. So he did his whole studies for 4 years of his PhD on chocolate. And he was just studying the structure at the atomic level and at the nanostructure level to understand how chocolate melts. So he was being paid by Mars, the Mars company, not the Mars planet, the chocolate company, and he was studying at a high degree how the crystals, so you can see this formation of these white and black kind of formations around this picture. This is a high magnification, high resolution of chocolate. And you can see that there's these weird alignments. These are all chocolate crystals made of either fat or chocolate itself. And the amount, so the size of these chocolate crystals, the dispersion of it, the length of them is what actually gives chocolate a particular flavor. So they found out by the end of it that if you can manipulate how these crystals can form within each other, can melt together, and the type of shape that they take, actually means that the chocolate could melt more easily within your mouth, or it could have a better or worse flavor. And that's what they were trying to study, literally 4 years studying chocolate. That was incredible. Another amazing thing that they've done at Imperial again. So this was a friend of mine again. He's now a senior lecturer at a university in London who's working and was working studying dinosaurs. So he worked in collaboration with the Natural History Museum that provided him with some heart cells from dinosaurs. And they were literally looking at how in high resolution in optical microscopy and scanning electron microscopy, which is a technique that allows you to see things that are very, very, very small. He was studying how these cells, the heart cells within the dinosaurs, were actually disposed. And he published so many papers on dinosaurs. Again, another incredible thing that you wouldn't think material scientists would end up studying. But yeah. Another fun example that I always love talking about is smart fabrics. Now, smart fabrics are a thing that has been developed much more recently, and it's something that falls into the category of smart materials, which we'll talk about for a bit because that's my discipline. That's what I love doing. Anything that is smart materials really fascinates me, and I just enjoy the fun of all of these materials that I will show you today. So smart fabrics can be fabrics that can adapt to your own body. They can, for example, change shape or change with your heat, and therefore being able to regulate how hot or how cold you are. And some fabrics at the moment, they're being interfaced with particular tissues and with particular electronics, so that, for example, deaf people could be able to hear music for the first time by just releasing some waves within your body in particular places that allow you to be in a concert hall and actually be able to feel the music on yourself rather than needing to hear it. So this is one of the greatest advances of material science. You can help so many people with the research that you can do in these fields. The other thing is butterflies and seashells. You will be like, why would we even need to study butterfly and seashells? Because they're pretty? Actually, yes. The reason why they are so pretty and so colorful, it's due to a very particular microstructure that they have. So they might look so shiny and pretty, and this is only because of a very, very fine structure that these materials have. So if you look at the structure in this slide, you can see that all of these two different materials are formed in this kind of very, very small channels, which will be microchannels. They interact with light in a very precise way. This will give it an iridescent color, which will be what changes when you're putting it into the light or outside of the light. So one of the things that I wanted to show you to prove that this is actually the case, I might just stop sharing so that you can see me better. What I wanted to show is I have got here 2 butterfly wings. So this doesn't actually happen with every butterfly ever. So we've got these 2 butterfly wings. I hope you can all see them properly. This will be of 2 different colors, the blue one and the orange one. The effect that I wanted to discuss with you happens exclusively in blue butterflies. And why is that the case? So the blue butterflies are actually the only ones that have this particular microstructure. And we can demonstrate that by showing that their color is exclusively due to their structure. How do we do that? So I have got here some alcohol, which I'm going to take a tiny drop of. I'm hoping I'm not going to drop alcohol everywhere on my desk. So I'm just going to grab a couple of drops of alcohol, if I do manage to. There we go. And what I want to show you is that if we drop a drop of alcohol on there, the color will disappear, and it will not disappear if I put it on the orange butterfly. So you can see that the moment I drop some alcohol here, the butterfly will become black. And why is that? This is happening because the alcohol is capable of infiltrating through those very, very small, tiny channels that the butterfly has, and therefore completely hiding and masking its color. The good thing is that once this is going to get dried and the alcohol evaporates, this is going to get back to its original color because I haven't actually affected the pigment. The butterfly doesn't have a pigment on itself. It has only these micro small channels that will change color because of the structure of it. So how can we, as material scientists, can take advantage of it? What do we do with it, basically? Well, we have been using it for particular light diffraction techniques. One of the ones that we can do is we can then take inspiration from nature and create a material that would do similar things. For example, I have this piece of plastic, which hopefully you'll be able to see how beautifully bifringent it is. So how it can just show incredible colors. And this is all created by having a very small micro pattern onto it. Even though you cannot feel it, you cannot see it at the naked eye, you can see that it creates these beautiful colors. And this is all due to a very fine microstructure that scientists have been able to recreate, which very, very closely mimics, I'm going to share the screen again, which very closely mimics the shape of butterflies. There we go. So this is exactly the shape that we're recreating with that particular material. And that's incredible. It's just such a nice thing to be able to go into a natural material and then transform it and take it and use it for your own applications. After that, another fun example is, which you've probably heard of because it's been used so much, is super light materials like aerogels. Now, aerogels are extraordinarily expensive, even though they are literally the lightest materials on earth. On this part of the slide, you can see this is an aerogel, which is made by silica. So it's kind of a glass. However, the way that it works is that by creating the highest amount of porosity ever, so you're creating loads of mini bubbles and holes within this whole structure, you're making it extraordinarily light, and you're also making it extremely good at thermal insulation. So you can see that this guy, crazily enough, has got his end on top of this slice of aerogel, and it's got a flamethrower under it, which is probably not a flamethrower, but he's got an active flame under it, which is going to be hot. And you can leave your hand on top of this material for as long as you want. You're not going to get burnt. And this is due to the very, very fine structure that you have in these materials. And you can make them of different materials. For example, the one on the right-hand side is a graphene foam. And this graphene foam is, again, extra light, and it's incredibly good at conducting electricity. And it has been used for sensing skin, for example, or it's been used in aerospace applications as well. These materials are all things that we can develop and study within material science by tailoring and fine-tuning the microstructure that we can get from a simple material like glass or from a more complicated material like graphene. So another example, this is one of the examples that I love the most. I've done most of my works on this. These are self-healing materials. Some of you will have heard of them. These materials are incredible. They are capable of literally reforming once you've broken them. So you can take a material, you can cut them apart, you just join them back together, and they will reform immediately. Well, immediately. They might take a bit of time, but that time would be like 1 to 2 hours. And to give you an example of these materials, for example, we've got silipatti, which some of you might have heard of, also called oobleck, maybe, I think you call it oobleck. So silipatti itself, you know it because it's fun, because it bounces, because it's just this squishy and extraordinarily like malleable material. However, if you cut it in half and then you put it together, even just for a second, it will be able to reform really, really quickly. And this is due to the bonds, to the chemical bonds that are inside this material. And you can see that it's reforming this very, very fine bonds. And this is literally due to a particular bond formation at the molecular level of these materials. So you didn't know, but a lot of materials that you've been playing with are self-healing. Clearly, this is a very light material. It's not very strong. But what you can do is can make materials that are way, way stronger than that, like the one in that particular slide, or another one that I have here, which is similar to the material in that slide, and is, where is it? Is this material here, for example. So this is a similar thing. It's still a self-healing material. This has been cut once, if you can see it in that small part. It's been joined again, and now you can't really separate it anymore. So you can make materials which are very strong but self-healing again. So imagine the fabulous potential that these materials will have once you use them for fabrics, once you use them for armor, once you use them for materials where you don't need to go there and fix everything. So this is extremely useful for a circular economy, for example, where you can reuse your materials rather than just throw them in the bin. And these are a fabulous example of that. Another thing and another smart material that I've been working on a lot are shape-changing materials. So this is, probably some of you will have seen this again. This is a particular metal, which is called nitinol. And in this case, from the video, you can see that this metal has been shaped into a spring. However, if you can place it in hot water, really, really quickly, it will go back to its initial shape. And let me show this to you again. And it's incredible that a metal that is quite strong would be able to change its shape so quickly. And what we can do now with these types of metals is that we can have more than one shape change. So you will have springs that are capable to extend and contract and re-extend and contract based simply whether they're exposed to heat or cool. So if you're putting them in hot water, they will extend, and if you're putting them in cold water, they will then contract. They are fabulous, and NASA is using these springs as well to create, for example, tires that could go into space and be modified by just NASA applying heat on them remotely. So this is one of the videos that I wanted to show you. It's really, really amazing what they can do with this technology. It's about 1 minute, so stay with me.
This particular tire, unlike a conventional spring tire made of spring steel, is different because the material that it's made from is an alloy based on stoichiometric nickel titanium. And this particular material doesn't deform like conventional materials, where in those materials, when we put stress on them, we basically are stretching the bonds between the atomic structures. This material has a unique characteristic that allows it to do an atomic rearrangement to accommodate deformation. And that lets us do about 30 times the deformation we could do in a conventional material without having permanent deformation happen. We could actually deform this all the way down to the axle and have it return to shape, which we could never even contemplate in a conventional metal system.
Yeah, so pretty cool if you ask me. How do I get out of this? There we go. Another type of materials are sensing materials. In this case, again, another material that you might have seen, but you might just look at them as gimmicky materials, but these can actually allow you to, as material scientists, they can allow you to find the potential to use them in real life applications so much and so much in depth. So these materials, for example, are liquid crystals, which you might have seen before. So this is what they do. This is a sheet of a material which is basically in between a liquid and a solid, and its behavior allows its molecules to rotate in a particular way so that they reflect light in different directions. Of course, I've got a sheet of that here. So you'll be able to see it from this. My hands are a bit cold, but you should be able to see that this actually works. Hopefully, yeah, there it is. So with heat, all of the molecules will tend to arrange in a particular direction. And then once the sheet cools down, they will return back to their original direction. How are they done and how do they work? So you can see that these molecules they've all got this kind of rice shape. And when you're applying heat through them, you'll be able to align them all in a particular direction, which means that you'll be able to give them a particular wavelength to interact with, and that will respond with a particular color. So that's why you will be able to see different colors within these materials. Again, stunning, not only stunning, but clearly these can be used for colors, they can be used to determine temperature with a color change. And so they can be used as thermometers, as you might have seen in many like products for children or baths. And the other thing that these liquid crystals are used in, which again, you might have heard of, are liquid crystal displays, so LCDs. LCDs is exactly using a similar material to this, so they're still liquid crystals. And these liquid crystals, this time within liquid crystal display, they actually rotate depending on an electric field. So that's why I put the spark here, rather than a thermal stimuli. So what happens is that these will rotate depending on an electric field, and they will allow light to pass through or not pass through. And that's how you see black or you see color within an LCD screen. There will be more on this. If you want, there will be a link, a video linked at the end of this talk, where you can go and see how liquid crystals work in a bit more depth to it. But this was just a general outline of it. So we don't just play with cool materials, even though I've shown you that some materials are really useful and even NASA is using them. We also save lives by doing material science. How do we do that? We have another study, for example, that was done at Imperial. This was from Dr. Tamara Chapman, who's now working at Royce. Basically, what happened here, we had Tamara and Royce that came to Tamara and they told her, okay, we have a problem. It's called the blue dot problem. And we have a problem that our metal is getting corroded when passing through air that contains salt. So when they were passing through ocean flights, the particular metals of the blades, the turbine blades, were getting corroded by salt. And they needed to find a way to solve this problem, because this was stopping planes from flying in the same way, or stopping planes from coming back completely failure-free. So the problem of this corrosion would have meant that the planes could have had small cracks that could have then propagated afterwards. And what Tamara did, managed to, with really high techniques and resolutions microscopy, she managed to understand how this problem can be resolved. And this can be resolved by putting a coating that would then resist the formation of these cracks within your materials. So this was a fantastic thing that we managed to resolve within like a 3 years work, just because Rolls-Royce came to us and put a problem in front of us. And this is what we do daily. Another amazing thing that we do and we create is biomaterials, which they're on the news constantly, so you will have heard of them. We've got fabulous materials here, for example, where you can create a scaffold, which is basically a 3D model of somewhere where cells can grow on top of it. You might think it's super easy, but you need to find a way that your scaffold allows the cells to grow in and the cells feel comfortable within the scaffold. So it needs to be a very particular environment for the cells to fit in. And therefore we need to work a lot on how to determine what material is best to use, what fine properties it has to have, and what type of microstructure this material will need to have as well. We can also make fake artificial skin, which could use to replace skin that we currently have lost, or it can be used as robotic skin. And also another fabulous thing is Bioglass. Bioglass has been invented, it was the end of the 90s, I think. It was quite a long time ago, and not many people know of its existence, but it's this fantastic material that is capable of stimulating bone growth. So what happens when you have your bone has been broken, in a small area, you can put a piece of bioglass within, and it's called bioglass because it's actually made of glass as well. It's made of silica particles. You can put this material inside your body and it will be able to let the bone grow in it. And at the same time, the bone will eat this material to reform. And so by the end of it, you will be left with your whole intact bone, even though you had a broken part of your bone initially. It's fabulous. And one of the places that you can find this in is, for example, in the toothpaste called Sensodyne. I am not being paid by Sensodyne, so do not worry about that. Sensodyne actually contains, I think it's called noamine. So we've got very, very small particles of bioglass. And it's really good to strengthen your enamel, and that's why it's used so much. After I've told you all of this, and after I've told you how fantastically awesome material science is, you definitely want to get into a material science degree, right? I wanted to give you some information of how to join us in case you were planning to do that. So if you're still in school, you would need to look at A-level requirements that universities will have. Typically, you need to have an A-level in maths. And then depending on the university you go to, you have at least one of physics, chemistry, design technology, or biology. And the universities in our network, so our network pretty much encompasses and comprises all of the universities that do a material science degree. They are all over England, all over Wales, and we've got somewhere in Scotland. I'm sure that Chris will be able to mention that as well. And this is where you can find us. This is the Discover Materials network that we have. And to enter, you'd be able to you need to have an interview, a good application, and then English language. That's pretty much it. Shouldn't be too hard, right? And why would you enter into a materials degree, aside from the fact that it's so fabulously amazing and fun to study? It's also because it gives you amazing job opportunities. So what can you do with it? These are only a few of the different companies that our graduates go to work with. You got GSK, Roche, Rolls-Royce, BMW, Nivea, Airbus, Siemens. You can work in so many different fields. And if you don't want to work in a company, you can work within centers of research. You can work within university. You can work in so many different places, which are all incredible. And to do so, we've also sponsored a campaign to show how recent graduates and where they have been and what they are working in now. So this is Helen. She was a fantastic student a couple of years ago at Imperial, and she's now working at the Defense Science and Technology Lab. And she is just showing how fabulous her job is and how she's enjoying applying everything that she studied in material science and engineering until now. So that's pretty much all from me. I think I've bored you enough, hopefully not, with this talk about material science and how amazing it can be. And hopefully I've given you some hints of how good this can be. By the way, my butterfly has gone back to its original color in the meantime because the alcohol has evaporated from it. No, I haven't used a different butterfly. So if you're interested and would like to know more, please just get in touch with us. We're always happy to have as many questions as possible because we know that material science is not as known and it's such an incredible subject that everyone should know it. Hope you enjoyed it.
Thank you very much, Eleonora. That was absolutely fascinating. I can't see any questions in the chat, but one quick question. What is your favourite material?
I am Italian, by the way. I just like yes, if you couldn't have understood that from my accent, but yeah. Sorry, the question was?
Oh yeah, just before we head to the break, what is your favourite material?
Oh God.
Sorry to put you on the spot.
Don't do this to me. Oh my God, I literally don't know. Like, I love pretty much all of the materials that I've mentioned. I love. I think that Silly Putty is probably one of my favorite ones, because I used Silly Putty as an idea for my PhD. So I literally, one of the first materials that I managed to synthesize in a lab was Silly Putty, which might sound crazy, but I then used it to make a composite material that was extremely strong, that had layers in between this kind of brick and mortar structure of small layers of this polymer called Silly Putty, and it was fantastic at reforming itself. So you would break it, it had the strong bricks in between, you would put it back together and it would be as strong as the beginning. So yeah, I think it will have to be Silly Putty.
Awesome, thank you very much. There's one quick question that's come in. Do you know if there's any jobs in fashion for materials? So
I know that there are, basically throughout my years, I have worked with many students. One of them, for example, has gone into archaeology now because he loved the subject so much and he was capable of using all of its materials properties and its materials knowledge to then go into archaeology, which is nothing that we teach within material science. But since it's such a versatile subject, which teaches you so many different techniques, you can go do literally pretty much whatever you want. There definitely would be material scientists in the production of fabrics, because we are constantly looking for innovation within this field. So you would be able to look into how a new material or a new fabric or a new more sustainable material with woven plastic or a material that could self-heal again. We have been working on shape memory and shape-changing fabrics as well during my PhD. So there were definitely material scientists involved in that. And that was one of the cool things to follow as a project.
Awesome.